write correctly. G is abelian. If and only if GH squared is equal to G squared H squared for all G and H in the group. If and only if, remember that from discrete and maybe from 300. To prove an if and only if, we need to prove both ways, right? So let's first assume, I'll start the proof over here, that GH squared is equal to H, what do we do? G squared H squared. I want to show that that means the group's abelian. Well, by definition of all these squares, right, this is a shorthand notation. What really is GH squared in group notation? Remember, this isn't squaring in the regular sense, right? What is GH squared? Using my star operator.
G star H.
It's G star H star G star H, right? And this is G star G star H star H. That's what it means. Can I move the parentheses around? Big question. Can I? Yes, why? I'm in a group, right? So this is the same as G star H star G star H. And G star G star H star H, right? That's just moving the parentheses around because the group operator in a group is always associative. But now what can we do? What else works in a group? Everybody has a inverse. So that gives me what kind of law? Cancellation, right? Because I can multiply both sides by G inverse. So I can literally, in a group, I always have a cancellation law because everybody's got an inverse. I can just apply it that way. This means that H star G star H, that's all that's left over on this side, right? Must be the same thing as G star H star H. Now what can I do? Cancel the H's because I have a cancellation law in the group, and I have that H star G is equal to G star H, and these were arbitrary, right? Therefore, I conclude what? If H star G is the same as G star H for every G and H I pick, the group is abelian, right? Therefore, G is abelian. So that's one way, right? That's assume this one and get the other one. I think the other way is easier. Now let's do part 2 of the proof. This was part 1. Assume G is abelian. This one's easy then. G H squared is equal to G H G H. But G is abelian, so what can I do? I can swap the middle too, right? Done. It's easy when you assume abelian. Abelian groups are nice because everything commutes. So we've proven it both ways, and you always have to do that when you have an if and only if. You have to assume one side, show the other, and then reverse it. An if and only if proof is really two proofs. Usually one way is easy, and the other way is real work. Okay. So associativity is very, very important. Nothing works without it. That's why we demand it. It gives me associativity and inverses together. Let me do algebra. And algebra is why I like groups, because I can solve equations in them. All right. Let's look at the finite subgroup test, because it's a real pretty proof. Suppose G is a group. And S is a finite subset. There's a huge difference between finite and infinite. Finite makes things trivial sometimes. Finite subgroup means, right, not infinite, less than the total number of integers, right? So 50 elements, 100 elements, 1,000,000 elements, but some finite number. Then, if S is closed under the operator, the group operator, S is a subgroup. This is called the finite subgroup test. That's a lot easier, right? All I have to do is prove closure and I'm done. Why does it work? Okay, suppose we have these conditions and I start listing elements in S. So I'm going to choose H, some element H in S. What do I know immediately is also in S? It's the only element I've got, so what can I do? I can H star H, right? Then H squared, H cubed. Can I keep going forever? Can I keep going forever? Do I have to reach a limit at some point?
You have to if it's finite.
It's finite. So somewhere in the line, we'll call it H n. Somewhere out here, I have to have equality somewhere, right? Because if I keep going forever, I have an infinite number of elements, but I don't. I have a finite number, so eventually some element has to equal another one. One of the powers of H has to equal another one. Otherwise, I go on forever. I violate the finite condition. So for some n in M, H to the n must equal H to the n, right? I have to wrap around at some point, right? Well, then, if that's true, then H has an, let's see, can I do this? No, I don't know I have inverses yet. I need a better plan. This is the idea. Oh, simple. suppose that m is greater than n, as I listed it, right? Then pick another letter, L equals m minus n is greater than 0, right? So then, h to the L times h to the n, what would it be? Well, that's h to the m minus n times h to the n, and that's positive. I haven't done anything wrong. But what happens to multiply exponents? They add, right? That's equal to h to the m, right? So I found a way to rewrite the one with the bigger power this way. So now I have h to the n is equal to h to the m, which is h to the L times h to the n. And I can always throw on a group identity. I'm in a group, right? But now, the identity, which may or may not be an S, right, times h to the n is the same as h to the L times h to the n, but I'm in a group. So I can cancel. And indeed, h to the L must be the group identity. And it's in there. So I have the identity. What else do I need? I have closure, I have identity, I need inverses. Suppose I want to find the inverse of h to the m. Well, of h, right? H to the m is clearly h times h to what power? m minus 1, right? Let's use this one. L and L minus 1. But h to the L is e. So now I've got the inverse of h. H times h to the L minus 1 using the same L. H has an inverse, namely h to the L minus 1. This proof is outlined under the subgroup test in our book. But that's the idea. So finite subgroup, because I can't have an infinite number of different powers of the element, it has to cycle back somewhere, that forces me to have cancellation, identity and inverses. And so that makes testing finite subgroups really easy. Okay, one more topic. Out of this subgroup chapter. If G is a group, we define the center of the group, the center of G, denoted Z of G. It's Z because the Germans invented a lot of this, and Zentrum is 0, is center in German, is defined as the set of all elements in the group that commute with every element. Now, if the group's abelian, the center is the group, right? Because everything commutes with everything. But if it's not abelian, this becomes an interesting thing. So It's the set of all elements that commute with every element. It turns out this is a subgroup. And it's not only a subgroup, it's an abelian subgroup, which means if I have a non-abelian group, a non-commutative group, if I can find the center, I've gone from non-commutative to commutative, at least for a piece of the group, and that's what makes the center an interesting thing, because commutativity helps me solve problems. So maybe we can take the first step at showing that this is a subgroup. What's the first question for a subgroup test?
Identity.
Identity. Well, does the identity commute with every element in the group? If I take e.g., what do I get?
G.
And by definition of the identity, that's the same as
GE.
GE, because the identity has to work on both sides by definition. Therefore, E is an element of the center, not double struck. The center of any group. Okay, we'll pick up there on Friday. Keep working with groups and group problems. I'll be in my office from 2:30 to 4 today, or a little bit before 4, and all day tomorrow if you have questions on your take home. Let's kill the camera if you haven't yet.